Okay. So today we will discuss these compatibility relations. We'll continue the discussion. We were last time we had derived the compatibility conditions that del cross epsilon equal to 0. So if you have a single value displacement, then these relations are satisfied, and conversely, if these relations are satisfied for a simply connected domain, then there exists a single valued displacement field such that epsilon is equal to half of del u plus del u transpose. Right? So this we saw the last time. Now there is a lot of confusion regarding the compatibility relations. I mean, as recently as maybe 2000 or something like that, there were some papers by some Russian authors that claimed that only the first three of the compatibility relations need to be verified, and then the remaining three will just follow from that, and so on and so forth. So there is a lot of confusion in the literature about whether all the 6 compatibility relations need to be checked or only a subset of the compatibility relations need to be checked. So that is something we will discuss today. So let me write out the compatibility relations in the Cartesian coordinate system. So del square epsilon xx by del y square plus del square epsilon yy by del x square is equal to 2 times del square epsilon xy by del x del y, then del square epsilon yy by del z square plus del square epsilon zz by del y square is equal to 2 times del square epsilon yz by del y del z, del square epsilon zz by del x square plus del square epsilon xx by del z square is equal to 2 times del square epsilon xz by del z del x. So here actually, so once you know the first compatibility relation, the others are obtained simply by permuting the indices, right? So you x goes to y, y goes to z, y goes to z, z goes to x goes to y goes to z, and so on. So once you write down the first compatibility relation, then the other two are just obtained by permuting the indices. So x goes to y goes to z, z goes to x. Okay, then similarly, there are the other sets of compatibility relations, that is minus del square epsilon xx by del y del z is equal to, plus del y del x of minus del epsilon yz by del x plus del epsilon xz by del y plus del epsilon xy by del z equal to 0, and minus del square epsilon yy by del z del x plus del y del y of minus of del epsilon zx by del y plus del epsilon xy by del z plus del epsilon yz by del x is equal to 0, and minus del square epsilon zz by del x del y plus del y del z of minus del epsilon xy by del z plus del epsilon yz by del x plus del epsilon zx by del y is equal to 0. So again, if you write the first of these particular relations, which involves the shear components here, then again you permute x to y, y to z, you will get the remaining 2. So these are the 6 compatibility relations in the Cartesian coordinate system here. And so, so some of the claims in the papers are that you need to check only these 3, and then these will be automatically satisfied, or you need to check only these 3 and then these will be satisfied. So what I am going to show today is that actually you need to check all the 6. Okay, that is what I am going to show today. So that means you cannot simply check only the first 3 or only the last 3. Okay, all 6 need to be checked. So it can be that there is a violation only of one of the relations and the remaining are satisfied, and so on and so forth. So basically all these compatibility relations are independent in that sense. Independent in the sense that only one of them could be violated and then the remaining are satisfied. And that is what I am going to show here, right? So this whole confusion about whether all 6 need to be checked, we will resolve that confusion. So actually Southwell way back in like 1900 had shown that actually all these 6 compatibility relations are independent and they need to be checked. But somehow these recent authors, they have not referred to Southwell's work at all. That means they may be unaware of Southwell's work. So Southwell's work actually, but it's a very complicated proof to show that all the 6 are independent. But I will show you a much simpler method to show that all the compatibility relations are indeed independent here. So first, let us consider that epsilon xy is equal to xy, okay, and remaining 0. So you will see that if you take epsilon xy to the xy, then only the first compatibility relation is violated. Okay, so remaining 0 means the remaining strain components are 0. So only the first one you will see is violated if you take this as a strain field. Okay, but all the remaining compatibility relations you can easily verify that they all are satisfied. Okay, so only first one is violated. Others are satisfied. Okay, others are satisfied. Okay, so that shows that shows that this compatibility relation is independent of all the others. That means in the sense that it is giving a conclusion which the other compatibility relations are not giving, correct? Because these are all trivially satisfied. Okay, so they are saying that actually compatibility is satisfied, but this equation is saying that compatibility is not satisfied, right? Similarly, now if you take the epsilon yz, so second time you take epsilon yz is equal to yz, then third you take epsilon xz equal to xz. Then the fourth choice you make is epsilon xx is equal to yz. Then fifth choice is epsilon yy equal to xz. And sixth choice you make is epsilon zz is equal to xy. So you will see that if you make this choice, only the first compatibility relation is violated. If you make this choice, then only the second compatibility relation is violated. If you make this choice, only the third compatibility relation is violated. And if you make this choice, then only the fourth compatibility relation is violated, and so on. So basically, that shows that all of them are independent, right? Because so if I want to test this particular field, right, only the sixth equation is telling me that that compatibility is violated, right? So suppose if it were true that you need to check only these relations, right, and not check these relations, right, then we will never be able to figure out that this is an incompatible strain field, because these equations are saying that it is compatible, right? But it is this equation which is saying that this field is incompatible, correct? So that shows that actually all the six compatibility relations are independent of each other. Independent in the sense that you need to check all of them, and each one gives a piece of information that the other compatibility relations are not giving, right? Each compatibility relation is giving information which the other compatibility relations are not giving. So that is why you can see that actually all the compatibility relations are independent. So this is a nice proof to show that indeed you need to check all the compatibility relations here. Fine. And of course, again, in the literature, there are some other attempts to make it into three compatibility relations by coming up with a fourth order equation. So if you differentiate this del cross epsilon equal to 0 two more times, and then you will get three fourth order equations. Okay, but the problem with that is that this implies the fourth order compatibility relations, but the fourth order compatibility relations do not imply this. So we need the conditions to be completely equivalent, right? And so even those fourth order compatibility relations that you will find in the literature are wrong. Okay, so because as I said that this will imply the fourth order, but the fourth order will not imply this. Okay, so that is why those conditions, so they are not stated in all the books. Only in one or two books those fourth order conditions are stated, but those are also incorrect. So basically the conclusion is that you need to check all the 6 compatibility relations in order to verify whether a given strain field is compatible or not. Okay, so that is one thing here. Okay, so now we are in a position to write the equations of linear elasticity now. So let us do that. Yes, so let us do that now. So we'll assume that tau hat of I is equal to t hat of I is equal to s hat of I equal to 0. So that is the natural state, right? So that we'll assume here. And so assuming that, so let us call this as star. So assuming that star holds, we get that t hat of f is equal to c epsilon plus order of n. This c is that fourth order constitutive density, where epsilon is the half of del u plus del u transpose. Where epsilon is equal to half of del u plus del u transpose. So let us prove that. So proof of this. So t hat of f, so linearize basically. So this is equal to t hat of I plus del u. F is I plus del u. So this is equal to t hat of I plus d of t hat of I in the direction del u plus order of del u. Right? And then this is 0 because we have assumed that the reference configuration is a natural state, so there are no residual stresses. So this is equal to d of, so this is, or let me put that 0 plus this is c, the d of t hat of I is the constitutive tensor times del u plus order of del u. Right, and then since c c of w is equal to 0, right? This is something we have seen, right, for all w. So you can split this into a symmetric part and an antisymmetric part, and then c operating on the antisymmetric part is 0. Hence, you will get that c operating on the symmetric part of del u here. So this is equal to c times del u plus del u transpose divided by 2 plus order of del u. And so this is equal to c times epsilon plus order of del u. So this is what you will get as the constitutive equation for a linear elastic material. Okay, so one question that I will pose to you at this stage is that we have seen that c operating on this epsilon is a symmetric tensor, right? So c epsilon belongs to sim, right? But we also know that t hat of f, t hat is the first pure Kirchhoff stress, so that can be unsymmetric, right? So how do you resolve this particular issue here? That this part is unsymmetric, but this part is symmetric. So try to resolve this issue here. Fine. So okay, and then since c is also equal to d of tau hat of I, and is also equal to d of s hat of I, we will also have that tau is equal to s is equal to c epsilon. Within the linearized theory, we will also have this particular relation here. So within the linear theory of elasticity, the first Kirchhoff stress the second Euler-Markov stress and the Cauchy stress, they are all the same within the linear scale. That is why you will see that again, books on linear elasticity such as Timoshenko and Goodyear, they don't talk of multiple stress values. So like we do in the nonlinear case, we have a Cauchy stress, we have first Euler-Markov stress, second Euler-Markov stress. So they will just talk of stress tensor, right? So that is because all of them will give you the C epsilon here. So let me just write that here. So within the linear context, right, within the framework of linear elasticity, framework of linear elasticity, the Cauchy first and second Euler-Markov stresses are identical. That is because, see, basically we will ignore this particular order value you are ignoring, and so all of them, D, S, and this one, they will all give C of epsilon there. Okay, and fine. So let us write now the equations of linear elasticity now. So we will get that rho naught times del square u by del t square is equal to del dot t plus rho naught b naught of x comma t. And this b, okay, we'll get that. So suppose if you linearize this b naught of x comma t is actually b of chi of x comma t comma t. Right? And so if you linearize this particular term here, so you will get that b of x plus u comma t is equal to b of x comma t plus del b times u plus order of it. And then this term we are sort of neglecting because, so as I said, in the linearized case you will neglect this term, and so you will take the body force on the reference configuration. So that I have already given you this example that suppose if you have a spinning rod, right, and then this is rotating, then you will consider the body force only on this reference configuration. So actually there will be an extension of this, right, because of the centrifugal force. And then you have to consider, actually in the nonlinear context, you would have to consider the body force on the deformed configuration. But in the linear case, everything, we are just considering the body forces, the tractions, everything only on the reference configuration. So that is why U has to be small. So that is what I said, that most of the books, they just mention that del U should be small. But actually, not only del U, but even U should also be small in the linear theory of elasticity, because as you can see from this, you are neglecting this particular term, and then you are writing all the body forces with respect to the reference configuration alone, right? So that's and as I said, the same thing for tractions also. So that is what we have. Fine. So so now you can write your linear equations as follows. So actually these were the nonlinear equations, right? So this is the nonlinear equation, nonlinear, and now we will get the linearized form from this particular thing here. So what we will get is that let us write it. So you will get that rho naught now del square u by del t square is equal to del dot t plus rho naught times b of x comma t, because we are considering only this particular term here, right? So that's why, as I said, that now the body force is taken only on the reference configuration, and then the constitutive relation is equal to C in the direction of epsilon. So this is the usual linear constitutive relation, and epsilon equal to half of del U plus del U naught. Okay, so these are the governing equations, and then these governing equations have to be solved subject to appropriate initial and boundary conditions here, right? So that's why, that's what I was giving this example of this rotating rod here. That if you consider this rho r omega square, so this body force will be applied only on this L, actually it should be applied on the deformed configuration, but in the linear case we will apply it only on this L. Suppose if L is the length of this particular rod, we will apply the body force only on this L. So all the integrations and all that will be carried out only with from 0 to L, not from 0 to L plus delta. Okay, so in the linear context. So that is the important thing here. Okay, so the last topic within this linear elasticity context is that we will show that the equations of linear elasticity do not satisfy material framing difference. Okay, so that is something, it's a very, very important result. So we will show that. Theorem. So T is frame different, and linear in F if and only if T hat of F is equal to F times T hat of Y. Okay, so this is a result that we will show. Okay, so we can see that F star is equal to QF, correct? And so T hat of QF is equal to Q times F times T hat of Y, which is equal to Q times T hat of F. So it is clear that if T hat of F is F times T hat of Y, then material framing difference is satisfied. Okay, so that is obvious. Now let us try to show the converse implication. That means that if T hat is framing different and linear in F, then it has to be of this particular form. So let us try to show that. So proof. As I said, that in one direction the proof is trivial. So I will show the proof in the other direction here. So let W belong to skew, and let Q be equal to identity plus sine alpha by W times W plus 1 minus cos alpha by W square times W square. And we are also given that T hat of QF is equal to Q times T hat of F. This is the condition for material framing difference here. Fine. So if you now substitute for this Q, right, into this particular equation and use the fact that it is linear, then what you will get is that sine alpha by W times T hat of W F plus 1 minus cos alpha by W square times T hat of W square of F is equal to sine alpha by W times W of T hat of F plus 1 minus cos alpha by W square times W square of T hat of F. So just all I have done is that I have used the linearity of the tensor of the mapping, and I've just simply substituted for Q into this particular relation, and then this is what you will get. So now you differentiate this relation with respect to alpha and evaluate at alpha equal to 0. So differentiate with respect to alpha and evaluate at alpha equal to 0. Evaluate at alpha equal to 0. Then what you will get is that T hat of WF is equal to W times T hat of F. Okay. So let us call this as let's see. So we will call this as star, and let us call this particular relation as double square. So so what you can see is that not this particular relation. Sorry about that. So let us call this as star and this relation as double star. So now you can see that T hat of WF is equal to W times T hat of F. We have shown. So this term is going to get cancelled with this term, and then if you choose any value of alpha where this whole thing is non-zero, then you will get that T of W square F is equal to W square of T of F. So from star and double star, so from star and double star, what you get is that T hat of W square of F is equal to W square of T hat of F. Okay. So what we have got now is that T hat of WF is W times T hat of F, and T hat of W square of F is W square times T hat of F. Okay, so now let us proceed. Now let W be equal to E2 dyadic E3 minus E3 dyadic E2. Okay, so this is the canonical, or this is an orthonormal system basis. E2, even E2, E3 is an orthonormal basis, and this is clearly a skew-symmetric tensor. So W square will be equal to minus of E2 dyadic E2 plus E3 dyadic E3, which is equal to E1 dyadic E1 minus identity. Okay, and then so what you will now write is that so let us call this relation now as 3 star. This one is 3 star. So from 3 star now, what you will get is that so from 3 star, what you will get is that T hat of E1 dyadic E1 is equal to E1 dyadic E1 minus times T hat of the identity. So this is actually what I have done is that I have already used the linearity of T hat. So there is this additional term, so T hat of I, that will get cancelled on both sides. Okay, because when you substitute it into this, then this is what you will get here. So I will actually this is from 3 star with F equal to identity. Yeah? So this is with F equal to identity. So I am taking F equal to identity in that particular relation. So T hat of W square is W square times T hat of identity. So I am just putting F equal to identity, and then you will get this particular relation here. Fine. So in the same way here also you can put F equal to identity and you will get T hat of W. So as a special case of this, you will get T hat of W is equal to W times T hat of I. Okay, so that is also something that you will get here. Now, okay, so what we have shown is that T hat of even dyadic E1 is even dyadic times this one, and then similarly, right? So similarly, let's erase this here. So similarly, you will get similarly T hat of E2 dyadic E2 is equal to E2 dyadic E2 times T hat of I, and then T hat of E3 dyadic E3 is equal to E3, that is E3 times E hat of I. Okay, so that is what you will get here. Okay, so now we write S as equal to, let me make some space here. So S is equal to summation of lambda I times EI star direct EI star, right? And so T hat of S is equal to summation of lambda I T hat of EI star direct EI star. So this is by the linearity. So T hat is a linear function and hence the lambda i's can be taken outside, and this is equal to summation of lambda I times EI star direct EI star times T hat of I, because that is this particular. See here, this E1, E2, E3, as I said, is an orthonormal basis, and so this is also an orthonormal basis, and hence we can apply these results to this particular case here. And this is equal to S times T hat of I. So what you get is that T hat of any symmetric tensor is the symmetric tensor times T hat of I. And then from this particular relation here, we also have, so this particular relation here, we have T hat of W is W times T hat of I. Okay, so now let us combine all these results and see what we get. So now F is equal to Fs plus Fss, and then now you get that T hat of F is equal to T hat of F of S plus T hat of F of Ss, and then this is equal to Fs times T hat of I plus Fss times T hat of I, because for the first part, this is the symmetric part of F and this is the anti-symmetric part of F. So the symmetric part of F, that comes from this, and for the anti-symmetric part, that comes from this one here. And then now combine the two, so this is equal to Fs plus Fss times T hat of I, which is equal to F times T hat of I. So what we have shown is that a constitutive relation for T hat is linear in F and material frame indifferent if and only if T hat of F is equal to F times T hat of I. Now, many times we have been assuming that T hat of I is 0, correct? That means the reference configuration does not have any residual stresses, and so basically what we get is that T hat of F is equal to 0, because so material frame indifference is satisfied if and only if the stress is 0. So obviously that is not going to be true, correct, in an actual situation. So basically what that says is that in any loading condition, right, your material frame indifference is going to be violated. Okay, so that is so you cannot have a relation that is linear and material frame indifferent in the linear context here. So even though the linear constitutive relation violates material frame indifference, still we adopt it as an approximation. Okay, so that is what we have to bear in mind here. So let us just look at all the relations in the linear context, right? So we have seen that this epsilon equal to half of del u plus del u transpose, right? So this does not vanish, right? Does not vanish for a rigid motion, right? For a rigid motion, and so you'll see that so this is also an approximation, right? Because we have neglected the del u transpose del u term, so that is why it does not vanish even when the motion is rigid, right? That is one shortcoming, and then T hat of F not satisfy MFI, right? Does not satisfy MFI, and so on and so forth. So, right, there are lots of shortcomings in the linear model, but still we use it as an approximation, right? But still we use it as a good approximation, right? Good approximation, right? So this is important. So basically what, to summarize the situation, what we are saying is that the equations of linear elasticity do not satisfy the axioms of continuum mechanics, but nevertheless it is good as an approximation, right? Because it simplifies things, and when your deformations are small, or your and your displacement gradients are small, then you can use this as a very good approximation, even though it violates almost every axiom of continuum mechanics. Even then you can use it here. Fine. Then so the last thing here is the strain energy density function. So the strain energy density function W is half of epsilon times C times epsilon. So this is the strain energy density function, and typically you will assume this C to be symmetric and positive definitely. Okay, so that is why this whole thing is going to be a positive quantity for any non-zero strain, and it will be equal to 0 if and only if epsilon itself is equal to 0. So if you substitute the constitutive relation, so this is T hat, so this is T hat of epsilon, T hat of F is this C times epsilon. So if you substitute now the strain displacement and all these relations into the balance of linear momentum, then you will get the Navier equations of elasticity. So lambda plus mu del of del dot u plus mu times del square u plus rho naught u naught. Okay, so that is what you will get as the Navier equations of elasticity, right? Navier equations of elasticity, right? So this is what you get. And so you have already seen how to solve, for special cases. I mean, for special problems rather, in the preceding course, right? Like solid mechanics type course, you have seen how to solve this using either the plane stress, plane strain assumption, or axisymmetric, or various kinds of assumptions, and then we have seen how to solve this in that particular course. So here my purpose was just to show how to obtain the equations of linear elasticity by a systematic linearization of the nonlinear equation. So what we have seen is that in the nonlinear context, all the equations are nonlinear, and every single aspect. So we have seen that the strain displacement relation is nonlinear, the constitutive relation is nonlinear, the governing equation is nonlinear, the boundary conditions are nonlinear, and so on. So by a systematic linearization of all these various aspects, we get to the linear theory of elasticity. So that is the idea here, and as I said, that it violates most of the axioms, but we still adopt it as a good approximation here. Okay, so we are not going to continue the discussion on the linear elasticity part anymore. So we will go to the next topic, which is the sort of very important topic of thermomechanics now. So we will start on that particular topic here. So thermomechanics. So first, we will derive a very interesting result. So far you have seen that we have applied this principle of frame indifference, right, only to the balance of mass, balance of linear momentum and balance of angular momentum. We have not yet applied it to the first law of thermodynamics, right? And so what we are going to show is that if you apply this frame indifference, so what do we mean by frame indifference? That the balance laws have the same form in all frames of reference, right? So we are now going to apply this to the first law of thermodynamics. So if we now say that the first law of thermodynamics has the same form in all frames of reference, then we will be able to deduce the balance of mass, the balance of linear momentum, the balance of angular momentum, the Cauchy principle, so all that will just fall out. So that is, it's a very interesting result that we are now going to derive. So that is the first thing we are going to do. And then after that, we are going to apply the second law of thermodynamics to compatibility relations. So basically, we will look at only two cases, which is elasticity and fluid mechanics. So those are the only two cases that we are going to consider as far as the second law of thermodynamics is concerned. But first, let us look at the implications of this frame indifference on the first law of thermodynamics. So frame indifference, indifference applied to the first law. Thermodynamics. Okay, so let us look at what the first law states here. So d by dt, we have seen that d by dt of integral of rho times e plus b dot b divided by 2 times db over v of t is equal to integral of t dot b plus gamma times ds over s of t plus integral of rho b dot b plus qh times dv over v of t. So here actually instead of putting q dot n, I will put gamma. Okay, so we are not assuming now that you can write this gamma as q dot n. Okay, so that is something we will deduce now from by applying frame indifference to this first law of thermodynamics here. So this is let us call this as 1, and assume under the change of observer. So assume that under a change of observer, we will assume that rho star of x star comma t star is rho of x comma t, then e star x star comma t star is e of x comma t, then gamma star of x star comma t star is equal to gamma of x comma t, then qh of x star comma t star is equal to qh of x comma t, t star of x star comma t star comma n star is equal to q of t times t of x comma t comma n, and b star minus a star is equal to q times b minus a. Okay. So actually, see, these are all physical scalar variables, right? And so we are assuming that the same density or the same internal energy or the same heat input is observed by both the observers. Okay, so these are sort of reasonable assumptions to make that two observers are observing the same scalar physical variable, right, at a given point. And then we are also assuming that the traction is objective or frame indifferent. So we have already discussed the motivation for that by considering the spring example, right? So that is also a reasonable assumption. And we are also assuming that this b star minus a star is q times b minus a. So actually this may be a little bit of a strong assumption in the sense that we know this from the balance of linear momentum. But okay, we will still assume this particular thing. Okay, and now under these assumptions, now let us see what the implications of frame integrals are. Okay, so let us say here now, so let 1 hold. So that means the first law of thermodynamics, let that hold. Then assume that under a change of observer, assume that under a change of observer, one has the same form as the same form. Okay. So what we mean by the same form means that you simply replace these unstarred quantities with the star quantity. So you will get rho star E star plus V star dot V star by 2 T star dot V star and so on. So it will have the same form in all frames of reference. So as the same form, okay, and then there exists functions tau and q such that t is equal to tau n. So this is the Cauchy principle, and gamma is equal to minus q dot n, and conservation of mass, and balance of linear momentum, balance of linear momentum, balance of angular momentum, and balance of angular momentum. All the world. Okay. Conversely, if there exists tau such that t is equal to tau n, and all the balance laws hold, then one has the same form in all frames of reference. Okay, so this is the converse. So of course, if so the converse is easy to prove. That means if you assume that that there exists a tau such that t equal to tau n, and if all the balance laws hold, then this has the same form in all frames of reference. It's easy to prove, but the forward implication is quite difficult, and so let us try to show that. Fine. So we will start the proof now. So let us write this. So yes. So let us show this. Let f be equal to rho times e plus v of v divided by 2. So whatever was occurring in that integral. So 1 can be written using tt1 as integral or v of t df by dt plus f del dot v times dv is equal to integral of t dot v plus gamma times ds plus integral of rho times b dot v plus qh times dv. So let us call this equation as 2. So here one has to be very careful in this proof. Okay, so here you can see that I have applied already transport theorem 1. We cannot apply transport theorem 2 because transport theorem 2 depends on mass conservation, correct? And so we have seen that in the statement of the theorem we are trying to show that mass conservation also holds, right? So we are going to prove that prove the equation of mass conservation. So basically we cannot assume now that balance of mass holds, right? Because that is the purpose of actually this particular theorem. So transport theorem 1 does not depend on the mass conservation equation, but transport theorem 2 does. And so we can only use transport theorem 1. We cannot use transport theorem 2. Okay, so that is one very, very important thing to note at this particular stage. So using this we get transport theorem 1, we get this particular thing. And now we have said that the balance laws are the same form in all frames of reference. So what you will get is that you will get that since now rho star is equal to rho, then qh star is equal to qh and gamma star is equal to gamma. What you will get is that integral of df star by dt plus f star times del x star dot v star times dv over v of t. This is equal to integral of t star dot v star plus gamma times ds, this is over s of t, plus integral of rho times v star dot v star plus qh times dv over v of t. So let us call this as 3. Then this f star is nothing but rho star times e star plus v star dot v star divided by 2. So that is L star. So whatever are the unstarred quantities, you simply replace them by the star quantities. That's all, right? That's how we get the star form of all the governing equations here. Okay, then so 3 minus 2 now. So 3 minus 2 will give us integral of d of f star minus f plus f star minus f times del dot v. So here I am using the fact that del x star dot v star is equal to del x dot v. So this relation, so I can replace del x star dot v star by del x dot v. Okay, so that is what I am doing here, times dv, this times dv over v of t, this plus integral of t star dot v star minus t dot v times ds over s of t, plus integral of rho times v star dot v star minus v dot v times dv. So this is sorry, this should be equal. I'm sorry about that. So not a plus but equal here. And let us call this equation as 4. Yes. Okay. So now let us use the expressions for f star and f. So f star is given by this, and f is given by the same thing without the star quantities here. So let us find all these quantities and substitute into these and see what we get here. Yes. Okay, so LHS of 4, so LHS 4 is equal to integral of v of t times half of v star dot v star minus v dot v times d rho by dt plus rho times del dot v times plus rho by 2 times d by dt of v star dot v star minus v dot v times dv. So this is the LHS of 4. So that is after substituting for f star and f, I will get this particular result for this particular term alone. Okay, so that's what we will get here. And this I can now substitute for v star. Correct? So we have the relation between v star and v. So use that in terms of the skew. So this is v of t times q of v plus half of q dot x plus c dot times dot product with q dot x plus c dot plus into d rho by dt plus rho del dot v plus rho times v star dot a star minus v dot v. So this is what you will get, this times dv here. Yes. Okay. So now you substitute t star equal to q times t into this equation, and let's see what we get here now. So substitute now. Substitute t star is equal to q times t, and b star minus a star is equal to q times t minus a. So if you recall, these are the assumptions that we have made, right, while doing this particular theorem. And then if you substitute that into 4 now, into 4, then you will get the following result. Yeah, just write that. Erase all this. No. So you will get that integral of v of t times qv plus half of q dot x plus c dot of q dot x plus c dot times d rho by dt plus rho del dot v plus rho times q of a minus b dot q dot x plus c dot times dv is equal to integral of q times t dot of q dot x plus c dot. This is ds over s of t. So let us call this as phi, the fifth relation. And now this holds for all q. Okay, so this holds for all q belonging to what, plus, right? And also for all c of t. Okay, so we can choose now. So choose c equal to choose q to be identity. So choose q to be the identity tensor. So that means your q dot is equal to 0. And c dot equal to a constant vector. If you choose this, then what you will get is that from this particular relation, you will get an integral of v of t times v dot c dot plus half of c dot times d rho by dt plus rho del dot v plus rho times a minus b dot c dot times dv is equal to t dot c dot times ds over s of t. So this is what you get. Means if you just substitute q equal to identity, then all this q dot will go to 0, this q dot will go to 0, and so on. C dot you are choosing like a constant vector in this particular case here. And then so you will get this particular statement. Now you use the same argument that was used by proving the Cauchy theorem, right? That we had this tetrahedron and then we shrunk the tetrahedron, and so on and so forth, right? So that shrunk it to a point, and then from that we got the existence of the stress tensor, right? So we saw that there exists a stress tensor tau such that t is equal to tau n, right? So it's the same kind of arguments you can see. So this volume integral will go to 0, right? As you shrink that tetrahedron to a point, this volume integral will go to 0, and then from the surface term you will get the existence of the stress tensor here, right? So that's so those arguments are exactly analogous to what we did for the Cauchy principle while proving the Cauchy principle. So we will use that now here, and let us see what we get now. Okay. So we will get now the following thing. So so similar to the Cauchy principle proof, similar to the Cauchy principle proof, correct? You will get that there exists a tau such that t is equal to tau times n. And then now if you substitute this into 2, okay, so substitute, so that has erased here, but that was on the previous this one. So similar, so substitute this t equal to tau n. So substitute t equal to tau n into 2. Okay, so that is, and then you will get that there exists a vector function. There exists a vector function q such that gamma is equal to minus q dot. And this minus, as I said, that is just a sign convention that is preferred in the heat conduction community. But I mean, so as I said, that this minus, we are defining it in such a way that you are putting a minus sign. But I mean, one can of course have defined it without a minus sign as well. But that is done for convenience, so that your heat flux is in the opposite direction of the temperature gradient. So for that reason, we have put this particular negative sign here. So let us not worry about that negative sign, but there exists this function such that this one here. And okay, so now using this t equal to tau n, using now t equal to tau n and the divergence theorem and the divergence theorem. So the right hand side now of 5 can be simplified. Okay, so RHS of 5 now. So let us write RHS of 5, which is equal to, now let us write that. Just write that. So that is equal to integral of q times t dot q dot x plus c dot times ds, right? So this is the right hand side, and that is equal to, now put t equal to tau n, so that is q times tau times n dot q dot of x plus c dot times ds over s of t. This is equal to, use the definition of the transpose here. So you will get that this is tau transpose times q transpose times q dot x plus c dot n. So just use the definition of the transpose itself here, and then apply the divergence theorem to this. So this is del dot T tau transpose times Q transpose times Q dot of x plus C dot times dV. So, and now use the indicial notation and so on to simplify this particular expression. So you will get that this is del dot tau dot Q transpose times Q dot x plus C dot times dV plus tau matrix inner product of Q transpose Q dot times dV. So this is what you will get. And if you simplify this again using the definition of the transpose, so this you will get as Q times del dot tau dot Q dot of x plus C dot times dV plus integral of tau matrix inner product Q transpose Q dot times dV over V of t. So this is also over V of t. Now, so put this into 5 now. So wherever the right hand side now of 5, you can replace it with whatever I have derived here now. Fine. So let us write that. So substituting into 5 now. So substituting into 5, we get integral of QV plus half of Q dot x plus C dot times dot of Q dot x plus C dot times d rho by dt plus rho del dot v times dv is equal to integral of Q times del dot tau plus rho times v minus a dot of Q dot x plus C dot times dv plus integral, this is over V of t, plus integral over V of t of tau times Q transpose Q dot times d. So now you can see now you have mass conservation equation here. This is balance of linear momentum, and then this will give you balance of angular momentum in the form of the symmetry of the stress tensor. So you can see that all these objects are now appearing by imposing frame indifference on the first law of thermodynamics. So let us call this as 6. Okay. And now you choose, again you have to make intelligent choices for Q in order to deduce the next step in this. So let us do that. So what you will get is that choose Q to be I. So choose Q to be identity and Q dot equal to 0. And C dot is equal to lambda times E, where lambda belongs to R. Okay? So if you do that, and E is a unit vector, E is a unit vector. So if you do that, if you substitute it into this, then what you will get is that, so this is also V of t. So for V of t, what you will get is that lambda times V dot E plus lambda square by 2 times d rho by dt plus rho del dot V times dV is equal to lambda times integral of V of t times del dot tau plus rho times d minus a times dot e times t. And this we will call it as equation number 7 here. Okay, so So you now differentiate with respect to lambda, then what you will get, so differentiate with respect to lambda, and evaluate at lambda equal to 0, and evaluate at lambda equal to 0. No need of this, sorry. Just differentiate with respect to lambda, then what you will get is that integral, you need to, I think, let's see, yeah. So what you will get is that integral of d rho by dt plus rho times del dot v is times dv is equal to 0. So this is what you will get on differentiating it twice. Sorry about this. So differentiate. So this is actually twice. Sorry about that. Differentiate twice with respect to lambda. Okay. So basically, what will happen is that only this term will survive. This term will go to 0. This term will go to 0, and so only this will survive. And so then use localization. So this implies. So this is valid for all v of t. So by localization, you will get that d rho by dt plus rho del dot v is equal to 0. And then now you substitute this particular result into here. So this whole term now goes to 0. The left hand side goes to 0. Then you will get only this right hand side is equal to 0. Again, use localization, right? So from 7 now. So from 7. Now what you will get is that from 7 and localization, right, and localization, you will get that del dot tau plus rho times b minus a is equal to 0. So as you can see, now we have recovered the balance of mass and the balance of linear momentum. Okay, so now the only thing left is the balance of angular momentum here, right? So let's see. So this will call as 8, and this will call as 9. Fine. So yes. So let's see. Yeah. Yes, so if you now substitute, let's see, so if you now substitute 8 and 9 into 6, so you will get, so substitute 8 and 9 into 6. Okay, so that is this particular equation. So you will see that the left hand side, this left hand side vanishes, then this term also vanishes, so you will get only this particular term. So into 6, then what you will get is that integral of tau matrix inner product q transpose q dot times dv over v of t is equal to 0. That's what you will get now. And now you choose, okay, so let w belong to skew, and choose your q, and let q be equal to e to the w. Okay, so we know that this is a proper orthogonal tensor. Then from this we will get that q transpose q dot is equal to w. So from this we will get this particular result. And then if you now substitute it into this particular relation, then what you will get is that integral, so from this you will get now that integral of tau matrix inner product w dv is equal to 0. This is valid for all w belonging to skew, okay? Because we have started with an arbitrary w belonging to skew. Again, by localization, you will get that tau matrix inner product w is equal to 0 for all w belonging to skew, and then this implies that tau is equal to tau transpose. Okay, so that shows the symmetry of the stress tensor, and so that actually shows the balance of angular momentum. Okay, so basically to summarize now the whole situation, so by imposing the framing difference on the first law of thermodynamics, we were able to reduce the equation of balance of mass, the balance of linear momentum, that means del dot r plus rho times b minus a equals 0, and also the symmetry of the stress tensor. Okay. Conversely, if all of these things hold, then actually it is very easy to show that the first law of thermodynamics has the same form in all frames of reference. So that is quite trivial, but I will just mention it here. So conversely, if balance of mass, so if T is equal to tau n, gamma is minus q dot n, and del dot tau plus rho times b minus a equal to 0, and d rho by dt plus rho del dot v is equal to 0, then 6 is equal to 2 minus 3, right? So the 2 was the unstar form of the equation and 3 was the star form of the equation. So 6 represents the difference between 2 and 3. So if we show that 6 is 0, then that means they are the same form in all frames of reference, right? So here you can see that if d rho by dt plus rho del dot b is 0, if del dot tau plus rho times b minus e is 0, and then tau is symmetric, so this term is 0. So basically 6 is trivially satisfied, and so we will get that 2 and 3 have the same form here, right? So okay, so with these assumptions, right, you will see that 6 is trivially satisfied, and hence the first law of thermodynamics has the same form in all frames of reference. First law has the same form in all frames of reference. In all frames of reference. So we have shown the contours also. So yes. So as I said, that this is a very, very nice conclusion. So as I said, let me just summarize this whole situation. That if you impose the principle of framing difference, so basically we say that the form of the first law of thermodynamics is the same in all frames of reference. If we impose this condition, then we get balance of mass, balance of linear momentum, balance of angular momentum, the Cauchy principle, they all fall out of that principle. So we don't need to even adopt these axioms if we adopt that the first law of thermodynamics has the same form in all frames of reference. So as you can see, this principle of framing difference is really a very powerful principle, and that is the reason that we have adopted it in this particular course. So in the next class, we will discuss the second law of thermodynamics and the restrictions that are imposed on constitutive relations by the second law of thermodynamics. So that is going to be a very, very important topic, and we are going to apply it, as I said, to elasticity, to the case of elasticity, and to the case of fluid mechanics.